Hey there, I'm glad you're here. Tonight, let's drift into the quiet, strange beauty of the very small, leaving behind the comfortable, predictable world we can see and touch, and moving down into the realm of quantum physics. Everything in our everyday lives, from the stars above to the chair you are sitting on, seems to follow calm, consistent rules. Objects stay where you put them. They fall down when you drop them. And they move from one place to another along a clear path. This is the world of classical physics, a world we understand well. But when we zoom down, quietly and slowly, past the size of a human hair, past the size of a cell, and finally down to the size of an atom, all those familiar, consistent rules suddenly dissolve. The world of the tiny is not chaotic, but it follows a different, much more subtle kind of logic, a logic that is both profoundly beautiful and deeply counterintuitive, forcing us to rethink what reality actually means. It is a place of quiet possibility, governed by chance and probability, where matter behaves less like solid marbles and more like wispy clouds of potential, simply waiting for us to look at them before deciding where to be. The quiet understanding of this realm is arguably the greatest scientific achievement of the last 100 years, revealing a universe far more mysterious than we could have ever imagined, where even time and space begin to ripple and blur at the most fundamental level. To begin understanding this quiet world, we must first appreciate the concept that nothing in this tiny realm is continuous. Think about the energy in a light bulb, or the way an electron moves around an atom. In our big, everyday world, we assume that energy can exist in any amount, just as water can be poured in any quantity from a faucet. But the quantum world teaches us that nature has a subtle stop sign. Energy is quantized, which means it comes in discrete, fixed, tiny packets, like individual coins, instead of a continuous stream of fluid. The word quantum itself simply means the smallest possible amount of something, whether it is energy, momentum, or light. Light, for instance, which feels like a smooth, continuous wave, is actually delivered in little packets of energy called photons. Imagine the rain gently falling, but instead of a continuous drizzle, you realize that the rain is actually composed of individual, microscopic water balloons, each carrying a fixed, minimum amount of wetness. That single, fixed quantity is the quantum. And recognizing this was the very first step in unlocking the secrets of the atom. This idea of quantized energy is the foundation upon which everything else is built, suggesting that the universe operates less like a smooth ramp and more like a quiet, massive, and invisible staircase, where you cannot rest your foot between the steps. You must always be on one step or the next. The difference in size between these steps can be incredibly small, but the principle is absolute, confirming that nature has built itself upon tiny, fixed units. When we look at light or matter, we are always observing the sum of these individual, discrete packets. Isn't that fascinating? That all the smooth movement and continuous light we observe in our world is, at its heart, nothing more than the gentle chorus of countless individual, tiny packets of energy moving together, all following the quiet, fundamental rule that only certain specific values are allowed. This rule guides the entire structure of the atom, dictating where electrons can exist and how they can gain or lose energy, leading us directly into our next quiet discovery about how light and matter truly work at this deepest level. One of the most profound and quietly confusing discoveries in quantum physics is that the fundamental building blocks of the universe cannot decide what they want to be. They exhibit what is called wave-particle duality. When we look at light, for example, we know it behaves like a wave flowing across space, capable of being bent, reflected, and diffracted, just like ripples spreading gently across a pond. This wave nature is what gives light its color and its ability to spread out after passing through a tiny opening. But, as we just discussed, when light interacts with matter, such as when it hits a solar panel, it acts like a stream of individual tiny marbles, those discrete energy packets we called photons. It seems light behaves according to the experiment we set up, acting as a wave when we look for flow, and acting as a particle when we look for impact. Here's something curious. This duality is not exclusive to light. It also applies to matter itself, including the tiny electrons that orbit the nucleus of an atom. We naturally think of an electron as a tiny particle, a perfect, infinitesimal sphere with a fixed mass and charge, much like a tiny grain of sand. And yet, experiments have quietly and definitively proven that a single electron, when traveling through space, also exhibits wave-like behavior, capable of being spread out and diffracted just like a ripple in water. This means that a single electron does not always have a precise location. Instead, its position is described by a probability wave that gently spreads out over space. Imagine throwing that tiny grain of sand, and as it flies through the air, it simultaneously becomes a faint, ghostly ripple of potential, a cloud of possibility that suggests where it is most likely to be, rather than where it definitely is. This dual nature is not a mathematical trick. It is the fundamental, quiet reality of the quantum world. Every tiny bit of matter and every tiny packet of light is simultaneously both a specific point of mass or energy and a diffuse, spreading wave of probability. We do not experience this duality in our everyday lives because the wavelength associated with large, heavy objects, like your hand or a baseball, is so incredibly small that it becomes completely negligible. But for the electron, the wave aspect is large enough to fundamentally define its behavior. It is a beautiful, peaceful acknowledgement that the universe does not fit neatly into our simple, familiar boxes of thought. The electron's existence as a spreading wave, fundamentally changes how it occupies space within the atom, leading us to our next quiet chapter on how atoms are actually built. Now let's focus our attention on the electron, the tiny component that defines all of chemistry and binds atoms together into molecules. In the old, classical model of the atom, electrons were imagined to be like tiny, fast-moving planets orbiting a sun-like nucleus, capable of existing at any radius or at any energy level, like being able to stand anywhere on a smooth ramp. However, the quantum rules enforce strict, quiet order on the electron's life, and this order is defined by energy levels. Because energy is quantized, an electron cannot exist at just any distance or any energy around the nucleus. Instead, it is confined to specific, allowed orbits or shells, each corresponding to a fixed, discrete energy level. Think of the electron's life inside the atom as being restricted to a quiet, invisible staircase. The electron can stand on the first step, or the second step, or the third step, but it is absolutely forbidden from existing in the space between the steps. These are the allowed quantum states, and they are completely unique to each type of atom. This fact, more than any other, explains why every element on the periodic table is fundamentally different. Their atoms have unique energy staircases, which dictate how their electrons interact. An electron can move from a lower energy step to a higher energy step, but only if it absorbs the exact, precise amount of energy needed to bridge the gap between the two steps. It cannot accept too much or too little. Conversely, when an electron falls from a higher energy step down to a lower one, it must release the energy difference in the form of a tiny packet of light, a photon. This process is called a quantum leap, and it is the origin of all the gentle, beautiful colors we see in the universe. Imagine an electron falling from the second step to the first and quietly releasing a single photon of green light. Every element has its own unique set of colors, or spectral lines, which are simply the unique light signatures created by its electrons, making their very specific, quiet leaps between their strictly defined steps. This rule is so profound that it allows astronomers to look at the light from distant stars and quietly determine exactly what elements they are made of, simply by reading the colors of their electrons' gentle tumbles. Perhaps the most famous and quietly unsettling experiment in quantum physics is the double-slit experiment. It is a thought experiment that has been performed countless times in the real world, and it perfectly illustrates the profound strangeness of the quantum world and the central role that observation plays in defining reality. The setup is simple. Imagine a dark wall with two tiny vertical slits cut into it, and behind that wall, a screen to record where things land. First, if we fire tiny classical particles like grains of sand at the wall, they will go through one slit or the other, and create two dense lines on the back screen, exactly as you would expect, showing only particle behavior. Now, let's replace the sand grains with the quiet, tiny electrons. If we fire a stream of electrons through the two slits, what appears on the back screen is not two lines, but a complex pattern of light and dark bands, known as an interference pattern. This pattern is the definitive signature of waves interfering with one another, suggesting that the electron waves passed through both slits simultaneously. Just like ripples in water, this is the electron exhibiting its wave-like nature, spreading out and flowing through both openings at once. This result is already deeply strange, but the true mystery begins when we try to quietly figure out which slit the electron actually went through. If we place a tiny, gentle detector at one of the slits, a camera, for example, to simply observe the electron and definitively determine its path, a truly profound change occurs. The instant the electron is observed, the interference pattern on the back screen completely disappears, and it is instantly replaced by the simple two-line pattern we would expect from classical particles. The act of looking, the quiet act of measurement, forces the electron to abandon its spreading wave-like existence, and suddenly, instantaneously, commit to being a solid particle passing through one specific slit. It seems the universe is fundamentally ambiguous until we ask a precise question. This does not mean the electron is sentient or aware. It simply means that the act of observation, the physical interaction required to gain information, changes the system from a state of quiet possibility to a state of absolute certainty, showing us that the quantum world is intrinsically linked to how we choose to measure it. The discovery that an unobserved particle exists as a wave of possibility leads us directly to the bizarre and beautiful quantum concept of superposition. This is the idea that before a measurement is made, a quantum particle does not settle on one single state, but quietly exists in a combination of all its possible states at once. Imagine flipping a coin high into the air before it lands. It is simultaneously both heads and tails, a gentle blend of every potential outcome. This quiet state of existing in multiple places or multiple energy levels simultaneously is the definition of superposition, and it is the natural, unobserved state of all matter at the quantum scale. To illustrate this profound concept, scientists often refer to the famous quiet thought experiment known as Schrödinger's cat. Imagine a fictional cat sealed inside a perfectly insulated box, along with a radioactive source, a Geiger counter, a hammer, and a vial of poison, all set up so that if a single atom in the source decays, the hammer breaks the vial, and the cat is instantly killed. The single, crucial quantum event is the decay of that one atom. According to the rules of quantum mechanics, until the box is opened and the atom is observed, that atom exists in a superposition of both decayed and not decayed at the same time, because the atom is the trigger for the cat's fate. The cat, too, must exist in a superposition of being simultaneously both alive and dead, until the moment the observer opens the box. The point of this thought experiment is not about actual cats. It is a profound illustration of the moment the quantum world transitions into the classical world. It demonstrates that the rules of superposition are so fundamental that if they apply to an atom, they must logically apply to the larger, connected system of the cat and the box. When the observer opens the box, the act of measurement instantly forces the entire system, the atom, the hammer, and the cat, to collapse from a superposition of multiple possibilities into a single, definitive state. The cat is either quietly alive or tragically dead. The quiet reality is that all quantum events occur through the gentle math of probability, and the act of observation transforms that probability into certainty, marking the transition from the weird, quiet quantum world into the certain, definitive world of our everyday lives. One of the most profound and curious behaviors of quantum particles is something that is completely impossible in our everyday world, yet happens quietly and continuously millions of times per second. Quantum tunneling. In the classical world, if you throw a tennis ball against a solid brick wall, the ball will hit the wall and simply bounce back. It cannot possibly pass through the barrier. The wall represents a potential energy barrier, a hurdle the ball does not have enough energy to overcome. And in our familiar world, that is the end of the story. However, in the quantum world, the rules are different because the electron is also a wave of probability. When an electron wave encounters an energy barrier, a thin insulating layer, for example, most of the wave is indeed reflected back, just like the tennis ball. But here's the curious part. A tiny, small part of the electron's probability wave gently leaks through the barrier and appears on the other side. This means that there is a small but definite probability that the electron will simply appear on the far side of the barrier without ever having had the necessary energy to go over the top. This peaceful, gentle movement through a forbidden zone is called quantum tunneling. The particle has, in a sense, quietly borrowed the necessary energy for a fleeting moment to make the impossible jump. Or perhaps its wave simply smeared through the barrier. This curious phenomenon is not just a theoretical oddity. It is absolutely essential to the existence of our world and everything in it. For instance, quantum tunneling is the quiet engine that powers the sun and all stars. In the sun's core, hydrogen atoms must fuse together to create helium. But to do so, they must overcome an enormous natural electrical repulsion that acts as a huge energy barrier. The atoms do not possess enough thermal energy to overcome this wall classically. Instead, they quantum tunnel through the barrier, gently merging into a heavier element. Without this quiet, persistent tunneling process, the stars could not shine, and the universe would be a very cold, dark place. The same principle is quietly utilized in modern electronics, specifically in devices like flash memory, allowing electrons to tunnel into storage cells, demonstrating that the very foundation of our modern digital world relies on this tiny, impossible quantum leak. As we quietly examine the smallest particles, we must encounter one of the most fundamental and philosophically profound rules of the quantum realm: the Heisenberg uncertainty principle. In our everyday world, if you want to understand a baseball, you can easily measure its location and its speed or momentum at the exact same time with perfect accuracy. The act of measuring one does not affect the measurement of the other. The assumption is that we can know everything about an object simultaneously, given enough precision. The uncertainty principle teaches us that this assumption is deeply flawed in the quantum world. The principle states that there is an inherent, fundamental limit to how precisely we can know certain pairs of properties about a quantum particle at the same time. The most famous pairing is the particle's position and its momentum, its mass multiplied by its speed. The more precisely we quietly measure the position of a particle, the less precisely we are able to know its momentum. And conversely, the more precisely we determine its momentum, the more vague and uncertain its position becomes. This is not due to a flaw in our instruments or a lack of careful observation. It is a fundamental, quiet property of nature itself. The quiet, inherent reality is that when you precisely define one, you must allow the other to blur. Imagine trying to quietly measure the location of a fast-moving electron using a beam of light, a photon. To determine the electron's position accurately, you would need to use a very short wavelength of light. But short wavelength light carries a high amount of energy. And when that high energy photon strikes the tiny electron, the impact instantly and significantly changes the electron's speed or momentum. Thus, the very act of precisely measuring the electron's position fundamentally and immediately makes its momentum uncertain. If you try to use a less energetic photon to avoid changing the momentum, the longer wavelength makes the position measurement inherently imprecise. This quiet, unavoidable trade-off shows us that the quantum world is fundamentally fuzzy, confirming that a particle simply cannot possess a perfectly defined position and a perfectly defined momentum simultaneously. This principle imposes a deep, quiet constraint on our ability to ever fully know the precise, instantaneous state of the universe. Our quiet exploration of quantum strangeness brings us to arguably the most bizarre concept in all of physics: quantum entanglement. This is a phenomenon where two or more quantum particles become quietly linked in such a way that they share the same fate, no matter how far apart they are separated in space. Even if one entangled particle is here on Earth, and the other is quietly traveling on the far side of the galaxy. They remain instantly connected. Imagine you have two quantum coins that are entangled. If you measure one coin and find that it is heads, you instantly and absolutely know that the other distant coin must be tails, without ever having to look at it. The particles do not communicate by sending a signal back and forth. Their connection is instantaneous, defying the classical rule that nothing, not even information, can travel faster than the speed of light. This instantaneous linkage is why Albert Einstein famously and quietly referred to entanglement as spooky action at a distance, because it seemed to violate the basic principles of cause and effect in a local universe. Yet decades of quiet, careful experiments have definitively proven that entanglement is a fundamental reality of the universe. When you measure a property of one particle, the corresponding property of the other particle instantly and gently snaps into its complementary state. The reason entanglement does not violate the speed of light limit is subtle and quiet. While the particles' states are correlated instantaneously, we cannot use this connection to transmit any useful information. We cannot control which state the first particle will collapse into. It is always random, either heads or tails, and we only know the result after the measurement. Since the result is random, we cannot pre-program a message, such as heads means the message is 1, because we cannot force the particle to be heads. We only know what the second particle is after the first is measured. The quiet certainty of the linked result is only revealed after the fact. This means entanglement is an incredibly beautiful and mysterious correlation, a shared, instantaneous destiny between two particles that allows them to be treated as a single, quiet quantum system, regardless of the physical distance separating them. We have spent our time talking about tiny, discrete particles like photons and electrons. But to get a truly complete and quiet picture of the quantum world, we must move beyond the idea of individual particles and instead think in terms of fields. This deeper understanding is captured in the theory of quantum field theory, which quietly suggests that particles are not the fundamental things in the universe. Rather, they are simply ripples of excitement within continuous, all-pervading quantum fields. Imagine the universe is completely filled everywhere with invisible, quiet fields, like an incredibly vast ocean of energy. There is a field for electrons, called the electron field, a field for photons, called the electromagnetic field, and a field for every type of fundamental particle in existence. In this view, a particle is not a tiny, localized ball. It is simply a temporary vibration, or a small, energetic ripple that briefly pops up in its corresponding field. When a ripple in the electron field appears, we quietly observe it as an electron. When a ripple appears in the electromagnetic field, we observe it as a photon, a packet of light. The field itself is the primary, quiet, continuous reality, and the particles are the fleeting, temporary expressions of that field's energy. This view beautifully explains why all electrons, for instance, are perfectly identical everywhere in the universe, since every electron is simply a ripple of a single, universal electron field. They are all drawing their properties from the same source, much like every wave in an ocean is still fundamentally made of ocean water. Quantum field theory also helps to explain the quiet interactions between particles. Instead of two electrons exchanging an unknown force to repel each other, they are quietly exchanging a messenger particle, a photon, which is the ripple in the electromagnetic field. This exchange of photons mediates the force between them. This quiet shift in thinking, from particles being marbles to being fleeting vibrations in an all-encompassing energy sea, offers the deepest, most complete framework we have for understanding the entire quantum world, describing 3 of the 4 fundamental forces of nature, and providing a quiet, unified picture of the cosmos's most fundamental workings. As we gently conclude our story, we find that the profound strangeness of the quantum world is not just a subject for quiet theoretical thought, but is already quietly and deeply embedded in our everyday lives and promises to define our technological future. The quiet rules of the atom, which seemed so bizarre 100 years ago, are now the foundation of nearly every modern technology. For example, the laser, a fundamental tool in telecommunications, medicine, and manufacturing, relies entirely on the principle of electrons making precisely controlled, synchronized quantum leaps down their energy staircase, releasing identical, powerful photons of light. Without the quiet rules of quantization, the laser could not exist. Similarly, the transistor, the tiny switch at the heart of every computer chip and smartphone, relies on electrons quietly obeying the rules of quantum mechanics to perform its switching function, which is the technological application of the quantum leak we call tunneling. Looking ahead, the next great revolution promises to come from harnessing the most exotic quantum phenomena: superposition and entanglement. This is the quest for the quantum computer. Current computers, based on classical physics, store information as bits that are either a 1 or a 0, a simple binary state. A quantum computer, however, utilizes quantum bits, or qubits, which can exist in a superposition of simultaneously being both 1 and 0 at the same time. This quiet ability allows a quantum computer to explore many different possibilities simultaneously, leading to a computational power that grows exponentially with every added qubit, creating the potential to solve problems that would take even the most powerful current supercomputers millions of years to complete. Imagine the quiet power of a device that can explore countless different realities all at once. This future of quantum technology is already quietly unfolding in laboratories around the world, promising to revolutionize fields like medicine, materials science, and cryptography, quantum computers could help design new drugs by precisely modeling the complex quantum interactions of molecules, or create entirely new, stronger materials by simulating their atomic structure. They could also lead to a completely secure form of communication called quantum cryptography, which uses the quiet laws of physics to guarantee that any attempted eavesdropping on a message would instantly be revealed by collapsing the entangled quantum state. These advances confirm that the strange, quiet rules of the quantum realm are rapidly moving from the world of theory into the practical foundation of a profoundly different technological age, turning yesterday's spooky action into tomorrow's quiet certainty. And so, our gentle, quiet journey to the very small comes to an end. We've seen that the world of the tiny is not a place of confusion, but a realm of deep, beautiful probability, where particles quietly live in multiple states and instantly connect across vast cosmic distances. These are the subtle, profound rules that allow atoms to exist and stars to shine, confirming that the universe is far more mysterious and marvelous than we will ever fully comprehend. The universe is full of mysteries, but for now, let's rest under its quiet, steadfast light. May you find peace knowing that even the smallest things in existence are governed by the most elegant, gentle, and absolute rules. Rest deeply now, under the quiet, steady watch of the quantum world,